Greetings to you all. On this video, I'm going to focus on vapor pressure lowering as another correlative property. A vapor is a gas formed by boiling or evaporation of a liquid or sublimation of a solid. To clarify more about the vapor pressure lowering concept, let's consider this situation. When a solvent is in a closed container and it's allowed to evaporate and to reach a state of a dynamic equilibrium between the liquid and its vapors, the pressure exerted by the vapor in the space above the liquid is referred to as the vapor pressure of that liquid. So let's look at this diagram. We have a liquid that's blue in a closed container. Now it is a volatile liquid which can form the vapors above the surface of the liquid, and then these vapors that are created above the surface of the liquid, since they are in a random motion, when they hit the cover of the container, they come back and hit the surface of the liquid, and then the force or the pressure these vapors exert on the surface of the liquid is what we call the vapor pressure. It's obvious that the pressure exerted by the vapors above the surface of the liquid is directly proportional to the number of vapors created. The more the vapors are created, the greater the pressure they exert on the surface of that liquid. Experimentally, it has been found that the addition of any non-volatile solute to any liquid solvent reduces the vapor pressure of this solvent. So let's see, for example, here there is an apparatus that is used to measure the vapor pressure of a given solvent. When the solvent is alone, when it's pure, so the container is connected to a U-tube that contains mercury, and then the difference in the level of mercury in the U-tube is equivalent to the vapor pressure exerted by the vapors of this liquid. As you can see, the mercury column in the U-tube is not at the same level. There is a difference in the levels. So to this same liquid, there has been added a given solute. When a solute is added, you can see that now the number of vapors has reduced. And if you check even in the difference in the levels of mercury in the U-tube has also reduced, which means that when a solute is added to a solvent, the vapor pressure reduces. That's where it has been formulated a general observation that the vapor pressure is lowered by the addition of the solute. To calculate the vapor pressure lowering, we use Raoult's law. François-Marie Raoult is a French chemist who studied the behavior of different solutions and came up with a law that can be used to determine the molecular mass of different substances that are dissolved in the solution. It states that the vapor pressure of a volatile liquid in a solution is directly proportional to its mole fraction. Mathematically, Raoult's law is given by the vapor pressure of a solution. This is the vapor pressure of a solvent in the solution is equal to the mole fraction of the solvent, that's X, times the vapor pressure of the pure solvent, that is P solve. So the mole fraction is the number of moles of the liquid that you are finding the vapor pressure to the total number of moles of the solute and the solvent, meaning to the total number of moles of substances that are involved. That's what we call the mole fraction. The vapor pressure of a solvent in a solution with a non-volatile solute is always lower than the vapor pressure of pure solvent at the same temperature, as we have seen. So if this is the case, to find the vapor pressure lowering, we calculate the difference, that's delta P, of the vapor pressure of the pure solvent, which is always greater, minus the vapor pressure of the solvent in the solution, which is always lower. Since the vapor pressure is a colligative, vapor pressure lowering is a colligative property, we can also calculate it by taking the mole fraction of the solute, that's the amount of the solute, which is a mole fraction. As we have seen, mole fraction is the number of moles of that solute to the total number of moles of the solute and the solvent, then times the vapor pressure of the pure solvent before adding the solute. Example. We are asked to calculate the vapor pressure of a solution made by dissolving 50 grams of glucose, that's C6H12O6, in 500 grams of water. The vapor pressure of pure water is 47.1 millimeter of mercury at 37 degrees Celsius. So to solve this problem, we have to use Raoult's law that can help us to find the vapor pressure of the solution. So the vapor pressure of the solution is found by taking the mole fraction of the solvent times the vapor pressure of the pure solvent. Let's find the mole fraction of water. To find the mole fraction, we need the number of moles. First of all, the number of moles of glucose can be found by taking 50, that's the mass of glucose, over the molar mass of glucose, that's 180 grams per mole. Then we find the number of mole of glucose, that's equal to 0.28 mole. Then the number of mole of water is found by taking 500 grams, which is the mass of water, over the molar mass of water, that is 18 grams per mole. And then we find the number of moles of water, which is equal to 27.7 moles. After finding the number of moles, we find the mole fraction, which is the ratio of the number of moles of water to the total number of moles of glucose and that of water. So the mole fraction of water is equal to 27.7 mole, which is the number of moles of water, over the total number of moles of water and glucose, which is 27.7 plus 0.28 mole, and then we find 0.99, which is the mole fraction. It has no units because the units cancel one another. And again, you have to know that the mole fraction is always less than 1. So finally, we find the vapor pressure of the solution, which is equal to mole fraction, that is 0.99 times the vapor pressure of the pure solvent, that's for water, which is 47.1 millimeter of mercury, and then we get 46.63 millimeter of mercury. Example number 2 about vapor pressure lowering. We are asked to find the vapor pressure lowering, that is delta P, when 10 grams of glycerol, that's a C3H8O3, is added to 500 grams of water at 50 degrees Celsius. At this temperature, the vapor pressure of pure water is 92.5 millimeter of mercury. So to solve this, the vapor pressure lowering of this solution is found by using this formula, which is equal to the vapor pressure, the mole fraction of the solute, that's the glycerol, times the vapor pressure of the pure solvent, which is water. And then in order to find the vapor pressure lowering, we need first of all to find the mole fraction of glycerol. And to find it, we need the number of moles first. The number of moles of glycerol is equal to 10 grams of glycerol over the molar mass, which is 92.1 gram per mole for glycerol, and then we get 0.11 mole. The number of moles of water is equal to 500 grams over 18 grams per mole. That's the molar mass of water, and then we get 27.7 moles of water. And then the mole fraction of glycerol that we need to find the vapor pressure lowering is equal to number of moles of glycerol, which is 0.11 mole, over the total number of moles of water and glycerol, that's 27.7 plus 0.11 mole, and then we get 0.004 as the mole fraction of glycerol. Then to find the vapor pressure lowering, we take the product of mole fraction of glycerol and vapor pressure of pure water, which is 0.004 times 92.5 millimeter of mercury, and then we find the vapor pressure lowering, which is equal to 0.37 millimeter of mercury. So what you can see from here is that when 10 grams of glycerol is added to 500 grams of water, the vapor pressure of water is lowered by 0.37 millimeter of mercury. Thank you very much. I think you have got everything about the vapor pressure lowering as a correlative property.